The stage is yours.
Thank you so very much. So let me again start by sharing my screen so that everyone can see it. Yeah, so maybe let's recap what we did during the last 2 days. We discussed mathematics of deep learning, and then we said there's also deep learning for mathematics, but still right now we are aiming for developing or analyzing, let's say, deep learning techniques, improving them. We said that from statistical learning theory, there are these directions: expressivity, so the approximation error, then learning, so analyzing the training algorithm, and then also generalization. So how does it behave after training? How does the neural network behave after training on unseen data? And in my introductory lecture, I said there's another 4th point, which I find very exciting, and that's explainability. So explainability asks a bit different question. It asks the question, I have my neural network. Usually I don't know how it is trained. I just get it. Maybe I bought it in an algorithm, and I would like to analyze how it reaches decisions. So in that sense, opening the black box of the neural network by these explainability methods. And so the focus of this talk is on explainability. As you see, I mean, there are not many results, I mean, hard results like theorems and so on. And so I think from my perspective, it's a very exciting area, and it could actually use much more mathematical foundations. But yeah, so let me show what is there at this point. So what is the big question? As I said, I mean, we have a trained neural network. We don't know the training data, or I mean, how it was trained, which algorithm was used. And the question is, can we determine how it reaches decisions? In particular, what are the key features of my input data to reach a certain outcome? Why is it important? Well, I mean, let's say in various application settings. So for instance, I mean, you applied for a position and your application was rejected by maybe an automatic algorithm based on deep learning techniques, then you certainly might want to know the reason. And so then the person who handled the decision, or who handled, let's say, the process, needs to be able to ask the algorithm why this particular application was rejected. In addition, I mean, neural networks are very good also in determining pattern in large data sets. So then if it's used, for instance, in science, it might actually give some additional insight into the data, helping to analyze, I mean, analyzing how a decision was reached. And also in general, I mean, trustworthiness certainly, I mean, can be improved of all these types of algorithms if one can understand in a much better way how a network operates. So a vision for the future is certainly, I mean, one would like to ask any question to the algorithm and then also get a human-like answer. So one would like to be able to interact with the neural network concerning how it reached a decision, like you would interact with a human. But I mean, we are very far from that, as you will see. And there are various methods which have been suggested. So these are, let's say, main directions. There are, for instance, gradient-based methods, where just the gradient of the function is analyzed. Then there are so-called backpropagation methods, where basically what you do is you have your decision and you backpropagate it through the neural network to the initial input. There are surrogate model-based methods like LIME, and also game theoretic methods. And so since there is also a second talk by Klaus Robert Müller, and you see his name appearing in various instances, I mean, many of those you will also in particular hear then in his talk. So my interest is, I mean, to get a bit more, let's say, mathematical understanding of this whole area and whole field and how decisions are reached. And so what I would like to show you in this talk is a very general framework, which is based on information theory. And with this, you get maybe a bit more mathematical understanding of this explainability methods and the neural network. And these methods also show, and I will show you also various numerical examples, are extremely good results. So what is the main goal? So let's say I have a neural network which classifies digits. So let's say this network which I have, it says this is a 3. And now I would like to know how it reached this decision. And what I would like to know, for instance, is which pixels are most relevant for the decision. And then an explainability method could give me such a heat map. And that would tell me that these red dots, these red pixels, are very important for the decision, where the blue dots, the blue pixels, play against it. Yeah, and so this also makes a lot of sense if you take a closer look. Yeah, so these openings of the 3 are actually really important for distinguishing a 3 from an 8. So these pixels are actually very important. And maybe also this area here. Whereas, I mean, these parts here maybe play against it. Now, if you have a network which now wrongly classified this as an 8, then one would expect that the explainability method said, for the decision of the neural network, these openings were actually not that great. So this played against the decision, but maybe this area here was good and was something where the network also based its decision on to say that this is an 8. Yeah. So this is what is typically done. I mean, in particular in imaging sciences, getting these heat maps indicating which pixels are important. So this is typically what a classical approach is. However, I mean, one can also think of why should every pixel itself be important and maybe get, let's say, a relevance score. Couldn't it be that maybe also clusters of pixels are important, but not every single one? So for instance, if you look at a lake, at the water of a lake, so maybe the waves might be important, but not every single pixel is important, but let's say the combination. And so the question is, how can you get useful combinations of pixels? Also, one might want to incorporate additional knowledge of the problem, and maybe, which we will not treat here, but maybe also one would like to analyze how certain a decision is in the end. Maybe which areas, how certain the network is in certain areas. Yeah, so these are in some sense the challenges which, yeah, we'll see at some point during the lecture. So what exactly is relevance in a mathematical sense? Relevance of the input features. We will see that using information theory, we can define it precisely. What is such a good relevance map or heat map? We will see that we can formulate this as an optimization problem, which then is also open for analysis. We can compare relevant maps in a more or less fair manner. The question is also, I mean, not the whole world is imaging. There are a lot of other types of data which one might also use neural networks on. So the question is, can we also extend it to other modalities? We will see that this can be done. You'll see also numerical examples in that direction. And we will also see that, in particular, for instance, for imaging sciences, you don't need to treat every pixel separately, but in fact, it might be much better to treat also combinations of pixels and say maybe a certain combination of pixels is relevant. Okay. So as I said, I mean, this general framework, which I would like to introduce you to, is based on information theory, in particular on rate distortion. If you don't know what that is, that's not a problem. We will see that in a moment. So let me very slowly introduce you to that, at first on a very basic level, and then we will make it a bit more, let's say, mathematical. Okay, so this is the setting. I have a classification function. It could be a neural network, but it does not need to be, because for this type of algorithm, and it also distinguishes it, for instance, from these backpropagation algorithms, we don't, in that sense, use the inner structure of this classifier that much. Okay, so phi is the classification function, usually neural network, and then I have my input signal, and so maybe it maps this to 0.97, which then indicates that's a monkey, and this to 0.97, and this would indicate it is not a monkey. So what is the goal? which we want to achieve right now. I mean, it's a very modest goal. We just want to see which components or which pixels are relevant and which are not. Now, we don't want to give it a score, either it's relevant or not. So we want to determine the most relevant components of X for this prediction. And for that, so let's say this is my data X, my image. So I would like to analyze which are the relevant components, which are the relevant pixels. So let's assume these are maybe relevant without having a definition at this point, but it's a subset of the pixels here. Usually, I mean, as we aim for S to be small, I mean, we would like to have a concise explanation of the decision. And the complement we then also call non-relevant. So how do we determine what are the relevant components? So there we take what's called this rate distortion viewpoint. So what is rate distortion? So maybe just take a look at these two persons. They are always called Alice and Bob. And in information theory, this rate distortion theory does basically the following. Alice has a message. She sends the message or parts of the message to Bob, and she wants to send as few information as possible. So few information she sends, that's the rate. This should be small, but Bob should also get the meaning of the message, the entire message. So the error between the message Bob receives and Alice has, that's the distortion. So I'd like to keep the error, the distortion small, but also the rate small. Okay, and so now we transfer it to the setting we considered. So Alice has this image X, and let's say Alice also has the neural network. And we saw before the neural network applied to this image gave us 0.97. Now Alice needs to send something to Bob to deliver the message, and what she sends are pixels. So she sends now a partial image, namely these pixels S. Hopefully the relevant pixels. So then Bob receives these. He has now a slight problem. Sorry, I should say Bob also has the same neural network. But Bob has now a slight problem because this partial image, I mean, he cannot apply his neural network to. So what he needs to do is he needs to obfuscate to make it into a complete picture again, image. And then he can put it in his neural network and see the outcome. And so the question is, how do you obfuscate? It seems quite natural to do that with random pixels. It seems to least distort the meaning of these transmitted pixels. And so then, I mean, we get the decision. And so the question is, you see, I mean, the rate is now how many pixels are sent. The distortion is here, the difference between these. And this should be also small. And then if, let's say, this decision is approximately the same as here, then, I mean, these are really the relevant pixels. And so there were some first ideas in 2017 in this direction, which start basically this thread of research. There are different viewpoints you can take. You can optimize, for instance, for the smallest deletion mask so that the class score, so that the score here changes. Or you can optimize for the largest so that there is no significant effect. Sorry, for the smallest deletion mask, so for the smallest area here, so that the class score drops. Or you can ask for the largest part you obfuscate so that the decision remains the same. I said it wrong. Okay, so here what we aim for the largest deletion. So all the smallest number of relevant pixels, which is the same. Okay, so this we call Y, and now we can write down what Y is. So I have my classification function, I have my input signal, I have a random noise vector, then Y, what Bob receives is on S, it is X, and on the complement, it is this realization of this random noise vector. Then the expected distortion is the expected value of the difference, for instance, squared. And so what one aims for, as I said, is, for instance, we would like to, if the distortion should be bounded maybe by some epsilon, then we are looking for the smallest rate. So we want to deem as few pixels as possible to be relevant, but still the distortion should be under control. So in that sense, you can view this as a definition for a relevance map. Okay, so now we make it a bit more flexible, the framework, because what we also would like to now incorporate, for instance, is we would like to incorporate to also look at combinations of pixels. So right now, I mean, this, what I showed you is very restrictive. I just look at single pixels and I say the pixel is relevant or not. So first of all, I would like to maybe give also relevance score between 0 and 1 to each pixel. And second, I also would like it to be more flexible, for instance, to be able to handle combinations of pixels. Okay, good. So this I would call the general rate distortion framework. So first of all, I mean, let's look at data representations, because as I said, I mean, here we look at pixels, but we would like to make this a bit more flexible. So let's take an X in Rn, and so this is my data point now, and X I will now represent in this way. So this is a very flexible way. We have a function here, and then we have these different components. Now we will see in a moment how we can fill this with life. And later on, maybe already at this point, we will assign relevances to these components H1, H2, up to Hk. So the easiest example in this direction is the pixel representation, which is a special case of this, because if you just set f equal to the identity and the h is equal to xi, so then it fits in this framework. And here also the algorithm, as you just saw, assigns relevance scores to these hi's, which are here just the x. Yeah, so that fits very nicely in this framework. Okay, so the next, and since maybe you've thought back to the first lecture on expressivity, there we studied also representation systems like wavelets and shearlets. So how does this fit now in this framework? Well, it also fits in this framework because, I mean, these h's can also be the coefficients with respect to a certain representation, for instance, by wavelets or shearlets, which is then this f. So instead of a pixel representation, you can also have a representation by what one usually calls a dictionary, or think of it as a representation system. And it doesn't even need to be an osmolar basis. It can also be more flexible. It can be a redundant system. So in any case, we take, for instance, here wavelets or shearlets, but it can be any other system, something also more general. Then I can represent every signal in this way now. So then these h's are appropriate coefficients, and the f is now given by this sum over the psi j's. And again, we will assign the relevance scores now to these coefficients. Yeah, so these are two examples how you can fill this. So let me show it to you again. How you can fill this very general representation with life. But we would always assume that my f has such a representation, be it a pixel representation or by, say, something like wavelets or shearlets or something else. And again, the relevance scores you will assign to these h's. Okay. Good. So now, I mean, how do we obfuscate in a general manner? So again, let me assume that this is here my model or my classifier, or let's say the neural network I would like to analyze. I have my input where I would like to now analyze phi of x. Yeah, and let's assume x has such a representation, which we discussed just before. And I already said the relevance will be assigned to these vectors h. So the relevance score is a vector also in Rk, or here in 0, 1, k, because the relevance scores I would now for each of these h's assign to be between 0 and 1. Yeah. So if it's 1, it's really relevant. If it's 0, it's not relevant at all. And in addition, I take a probability distribution. Yeah, remember these HIs were in RDI. Okay, so now, I mean, I'll obfuscate in the following way. Think back of what we did before. Before we had our pixels and then we obfuscated the other part. Here now, since my S is not just 1 or 0, but a value between 0 and 1, it's a little bit more complicated. But so what we do now is the following. So what you see here as a component, first of all, you see here the relevance score S, and here 1 minus S. If each component of S is just either 0 or 1, we have in here 2 characteristic functions. But in general, it can be between 0. Then you have here these H's where you want to put the relevance score on, and here you have the obfuscation, these realizations of my distribution. Yeah, and so here you are now basically you have this weighted sum. So this dot product is, as you see, the component multiplication. So you have this weighted sum. So you multiply the H's with the scores. Before it was just 1 or 0. Here it could be also in between. And the for instance, noise, you multiply with 1 minus. And so then you apply the F, and this gives you Y. This is basically what warp risk is. So you see, it's a generalization of what we did before. Before S was just 0 or 1, and we also just had the pixel representation. So then the next is the distortion. So again, I mean, now I have my S, my mask, I have my X, my input vector, and I have this VS, this probability distribution. Then the distortion is now also very similar to what we had before. The expected value of the difference between phi of X and phi of Y. So now here, I mean, this can be any distance. So the question is also which distances choose. But then it's the expected value over all V distributed as Vs. Yeah, so that's the expected distortion. You see the components here. You have here the neural network. You have here where the distortion, where the obfuscation comes from. You have the mask, and you have here your input vector X. And then we define the RDE mask as the solution of this minimization problem. So what we now aim for is we want to minimize the distortion, as we also did before. And we want to do it in such a way that we get a concise explanation. And so this we achieve by minimizing the L0 norm. This we already saw before when we defined complexity of a neural network. So this counts the number of non-zero elements, and we want this to be less or equal than L. Yeah, so here we enforce sparsity in a certain sense. As you might expect, later on we need to relax this, but right now, I mean, this is what we aim for. So we aim for minimizing the distortion so that the number of relevant pixels or relevant H's is small. And so that you can also take a geometric viewpoint. You can interpret this RDE mask into a certain sense as a subspace. So this, if you look at the subspace, for instance, where you see, I mean, these were these obfuscations. When V now runs through the support of VS, then one can argue that that phi acts similarly on all of those if the distortion is small. So that's kind of like an invariant subspace to some extent. So let me show you also two pictures why this why the representation is so important. So this is a very tiny toy example. So you see, you just have 2 components here, and so this kind of bluish part here and here is this map. to the distance of phi of x and phi of u1, u2. And so here we have everything in Euclidean coordinates and here in polar coordinates. So what would happen now? I mean, we have here our input x. Let's say in the Euclidean domain it lies here, and maybe in the polar coordinates it lies here. And so now I'm wondering in which direction do I put my mask? I don't have many choices because I have just two components. So, and I mean, I could do it in this direction or in this direction. The same here. And what you observe, and now this color coding indicates, as you see here, the expected distortion in this direction for this mask and for this mask, and also the similar here. And what you observe is that if you now look at this polar coordinate viewpoint, that there the distortion is very small. So this would be now the preferable mask. And so sometimes if you look at different coordinates, you can get a much lower distortion just by a coordinate transformation. So that's kind of the message of this little figure. Good. So certainly, I mean, not everything, but a lot depends on how I obfuscate and how I perturb. So this distribution here. And so the particular choice which I select, that defines, as one calls it typically, an obfuscation strategy. And you have two different paths to take. This obfuscation can be either, one says, in distribution or out of distribution. So in distribution means that what I have here, so this was this obfuscation, which we saw already before. So it's this weighted sum. You see here S was again the mask. These H's were these components out of my data representation. The V was, for instance, a noise vector. And then F comes also from this data representation. So in distribution would mean that this obfuscation lies on the natural data manifold that phi was trained on. Out of distribution, we don't know. You see here maybe also a slight problem. So this in distribution, I mean, you need to know maybe a bit more about phi. If you don't know anything, you might need to go that route in any way. But often, I mean, this might be advantageous to obfuscate in a bit more smarter manner. Why? Well, I mean, as I said, I mean, the RDE mask depends on the evaluation on these obfuscations. So what could happen is that if this is not on the natural data manifold, so for instance, if you have images and now you obfuscate and it falls very much out of the data manifold of natural images, then it might be that the neural network there has, I mean, very strange reactions, because it's an area which is from a neural network viewpoint undeveloped. And so in that sense, it could happen that these explanations then are also corrupted. So that's something one need to think about. And if one has a bit of more knowledge, it is typically of benefit to choose BS so that this is always in distribution. So how can you do that? What you can do for that is you can actually train in painting gun. So a generative adversarial network, which we didn't discuss before. So what is this? So here, basically, what you aim for, you have here a generator, as you see, and you have a discriminator. And the generator generates images, and you would like to train it in such a way that the images which are generated are not distinguishable anymore from, let's say, a training data set. So usually, I mean, the discriminator would be able to say whether this is a fake image or a real image, but you would like to train this in such a way that the generator generates natural images. And so that's the way you can train for something to, in a certain sense, lie on a data manifold. And so now what you could do is, if you have, let's say, so you would now, you have your S, you have your mask, you have your H. These were the components from the data representation, and now before we had a V here. And so now one can train a gun to produce this part here, so that overall this lies on the data manifold. Yeah, or if you think back of this monkey where you had just one part, then yeah, so maybe it might be good to go back to look at this once. Yeah. So if you now have this part, you can train an in-painting gun to produce this remaining part here outside in such a way that it still looks maybe like a natural image. Yeah, so that's how you could reach in distribution obfuscation, if you have that knowledge about the natural data manifold. If you don't have this knowledge, I mean, there's not much you can do. Yeah, so then, I mean, you could choose Gaussian noise, as we did with the monkey. That's how you choose your VS. You could also, for instance, yeah, blur, let's say, the input in a certain way, so you can do different aspects. Yeah, so if you just blur, maybe it looks a bit more natural than if you just obfuscate it with random noise, and you saw then the image looks very unnatural in any case. So there are a lot of different strategies you can take and go in that direction. Okay, so which measure to take? So now, I mean, what we have, so maybe again, let's go back to our definition. Yeah, so now, I mean, we basically discussed, I mean, how to choose the V, yeah, so the VS. But the question is also how to choose this measure here. Because the measure is crucial for determining the distance between phi of x and phi of y. And so it's crucial for defining this, the expected distortion. Now, and so let's assume I have a classification task. So the classification task, usually, I mean, the output, I have different scores, not to confuse it with a relevance score. So here the classification, I have different, let's better say, outputs, and then I look at which output is the largest. And so this then gives me the class my input belongs to. And so what I can then do, for instance, if I have my input signal and I have another data point, I can just take the square distance in the predicted label. So that's one way to define a distance there. What I could also do is I could normalize my output to probability vector, and then I could also look at just the distance of these elements of now this probability vector. Yeah, but I mean, there are various distances you can take. I mean, this is the canonical one, and this we usually then also use in the experiments, which I will show you. Also, then you can also have a regression model. And here, for instance, you can take the R2 norm distance. That's one canonical measure. You can also, if you're just interested in, let's say, subsets, I mean, from, let's say, a coefficient or a coefficient viewpoint, then you can just also take the R2 distance just on parts of the output. Yeah, and also here, I mean, there are various measures which you can take. I mean, we usually go with this now also in the numerical experiments. Well, then you can ask, how is this actually implemented? And I already indicated one particular problem, namely this L0 norm. So that's what I showed you. That's what we aim for solving. But many of you, in particular those who know about the area of compressed sensing, know that, I mean, it's usually not possible to compute something like this. And we can also show that this problem is NPPP complete, and even computing approximation is NP-hard. So this NPPP complete is a special complexity class which belongs to artificial intelligence, where usually you have something where you plan under uncertainties. In any case, so this is a hard problem which we cannot compute. So the question is, what do we do? And the most canonical way is to do an L1 relaxation. So instead of the L0 norm to choose the L1 norm. Here with the Lagrange multiplier. So we solve the distortion plus lambda times the L1 norm of S of my mask. And so now you see this lambda is a means to put either more emphasis on minimizing the distortion or put more emphasis on getting a very sparse and concise explanation. Yeah, so that's a very classical approach to solve this. We have different ways to actually explicitly compute it then. I mean, we can, for instance, as it says here, the expected distortion, we can approximate by Monte Carlo estimates. And then we can also optimize then after that the mask by stochastic gradient descent. But the main message here is L1 minimization is typically the way to go. One can also follow different paths. One can also take, for instance, if you have a binary mask, we can view this as a Bernoulli random variable. So then, I mean, we would take the expectation just over this set again here with a relaxation by the L1 norm. And also there are different ways, I mean, to explicitly solve it, typically using components, aspects of stochastic gradient descent. And maybe the last, what you can also do is you can use an iterative procedure, starting with a zero mask and then updating the mask in each step until maybe you reach a mask which is reasonable and have some sort of stopping criteria. Yeah, I mean, that's, yeah, so in each iteration we have to test every entry of S, so that's sometimes a bit cumbersome. But I mean, in certain cases, this iterative procedure is also useful to pursue. Also, there are different ways to take, each following the same philosophy. Okay, so let's now look at some numerical examples. Now, so we start with a very classical, yeah, let me go back. We start with a very classical pixel-based explanation. So I have three types of numerical experiments for you. I mean, one is pixel-based RDE. We will then look at a representation in wavelets. And I will show you how this, let's say, wavelet RDE, how the results of that looks like. And then we will also look at different modalities. And I will show you some other examples, not images. Okay, so let's start with pixel RDE. Let's assume now I have a fixed neural network, which was given to me. It's a simple network. It does a very classical task. It classifies digits. It has a very high test accuracy. The image size is, I mean, for instance, in the MNIST database is 28 by 28. Okay, and so now, I mean, let's assume this is the image which is put in my neural network and it classified it correctly as a 6. Then you see here different types of explanations. And so you see here various different methods which you can apply. So this is the method we discussed. What you see nicely here is that it's a very concise mask. And also it nicely indicates this part, which is open, which in a certain sense, as we already intuitively discussed before, distinguishes, for instance, such a 6 from another number like an 8. But then, I mean, again, I mean, one can always look at it and say, I like this explanation better than the other. But what one can also do is one can compare it. And so this is one way to compare different approaches. So what you see here is the number of relevant pixels. Here you see the distortion, and you see that in a certain sense, I mean, our algorithm with a small rate has a very small distortion. Now you can say, well, this might be unfair with respect to the other algorithms because we actually optimize for that. But then on the other hand, if you look at other papers, which type of comparison measure they choose, then it's a similar comparison measure. Because, I mean, another comparison measure, what one could do is one can take, let's say, the pixels, sort them by their relevance, and then start at some point to flip the pixels. And then I flip and flip and flip, and at some point the decision will change. Yeah, and so then this is used as a comparison measure, and this is actually basically the same as what we use here as a comparison. Okay. You can do it a bit more complicated. You can go to SGL10. So there you have natural images. You see the images have size now 69 by 69. Again, I have a fixed neural network, which was generated for me by an unknown person. It has a high test accuracy, and I would like to analyze how it reaches decisions. And so, for instance, here we have this dog. It was correctly classified as a dog. And again, you see here different explanations. And again, you see here nicely how concise this explanation is. And basically it says, I mean, the algorithm looked at basically the shape of the head of the dog to be able to determine that it is a dog. And again, I mean, you can compare these different approaches, and not unexpectedly with small rate. I mean, we get here with our approach a very small distortion. Then here it deviates a little bit, which could also be due to the fact, I mean, remember we have this parameter lambda, which you need to choose in some way. And so how you choose lambda depends on at which rate basically the algorithm performs best and gives the best results. Okay, so these were pixel-based explanations. And I said one might wonder whether pixel-based explanations are the best you can do. Yeah, because in some sense, if you think about it, as I also said before, sometimes combination of pixels might be important, and each single pixel might not be relevant in any way if one does not take the context into account. And so what I would like to now show you is what we call wavelet RDE. So that's now based on, remember this general framework, we had pixel representation. So now we take a representation in terms of wavelets, and we will assign the relevance scores to the coefficients of that. And we called it then also cartoon X because basically the explanations look a bit like cartoon images. And so you can also actually, I mean, since wavelets, as we also discussed, come from compression, image compression, you can actually set this now also into relation, what we do with the explainability algorithm in relation to what a compression algorithm does, which is, you see certain, I think, interesting similarities. So here, I mean, in both cases, you have your input signal, you apply the wavelet transform. So this gives you a representation. And then typically here, you would select some entries, you select here also some entries, and then in the compression, what you do is the unselected entries you usually replace with just 0. And here you would replace it, for instance, with random noise, and then you map it back, and hopefully, again, here the philosophy is if the largest entries are most important for the image itself, then replacing the others with 0 doesn't really distort that much. Yeah, and so here, if we move back, this looks a bit strange because now we have replaced the others with random noise. Yeah, but I mean, then, I mean, what you see here, that's the reconstruction, that's the input image. You can look at the distance of those, and in compression, you certainly would like that this distance is very small. So minimizing this distance, as you saw here, is connected to selecting the largest entries. Here it's a little bit different, this part, because now we view the image through the neural network, through the classifier, both. And then we look at the distortion between phi of x and phi of y. And so then minimizing this d, so sorry, it's not the distortion, it's the distance. The distortion would be the expected value, the distance between phi of y and phi of x and phi of y. And so minimizing this would now correspond to selecting the most relevant entries. So in a certain sense, I mean, let's say the framework are to some extent comparable, only that now we view these images through neural networks. Okay, So then let's see how these images look like, these explanations. So here you have three, obviously, snails. You have a neural network which correctly classifies those as snails, and then what I show you here are different explanations. This is the pixel-based explanation, and you see it correctly, let's say, or what means correctly? I mean, it identifies certain pixels which seem to be important for the network. Yeah, and so the others are a bit more, yeah, different. I mean, either they mark a lot, or it's not really clear, I mean, which part are indicated here. What you observe now for this cartoon X explanation is that, in a sense, I mean, you seem to really see what the neural network saw to reach that decision. Yeah, so here you see, in a certain sense, the main part of the snake in, let's say, for the human visual system, much nicer manner, to understand why this decision was reached. Yeah, so in a certain sense, you can argue that the neural network saw here, I mean, this main part, but also here it saw a little bit like this round shape to reach this explanation. Yeah, so that already looks nice, but what we found actually quite interesting is then, I mean, if you look at adversarial examples. So adversarial examples we will discuss, I mean, in basically 1 hour when we come to robustness, but adversarial examples are examples where the network reaches the wrong decision. Yeah, and so the question is, how does the explanation then look like? And so here you have a network which reached the wrong decision on this image, and it classified this as a diaper. It reached the wrong decision on this and classified this as a microphone, and it reached the wrong decision on this and said this is a screw. So let's look at the first. So this was wrongly classified as diaper. If I look at pixel RDE, I mean, you basically, I mean, at least me, I don't know if you have, but I wouldn't have any idea why the neural network misclassified that. The same with also other types of explanations. But if I look at this explanation, you see it looks a bit like a baby. So then it's not that far to actually classify that image as a diaper. Yeah, so here I think one sees nicely how this now type of explainability algorithm, which uses a bit more sophisticated data representation, shows what the algorithm, what the neural network saw to reach this wrong conclusion. The same with the microphone. So also here, I mean, here maybe you see a bit, I mean, it's still not clear why this could be classified as a microphone. Whereas if you look at this, it looks really like a microphone. And so this shows, again, why this wrong decision was reached. The same with the screw. And so here, I mean, these algorithms basically fail completely, but this algorithm, you see, this has a structure of a screw. Yeah, so in that sense, I mean, involving more complicated representations of the data in combination with these information theoretic framework, you can unravel to some extent why sometimes things are wrongly classified. What also I think is interesting is that if you look at other types of explainability methods, sometimes they also invent edges, which you also might not want, because in a certain sense, I mean, you would like to have an explanation which part of the image is relevant, and you don't want that the explainability algorithm invents something in addition. And so you see this here. I mean, again, you see here these three images. You see the edges in the image. Sorry, you see the edges in the image. This is the cartoon X explanation of the decision, and you see the edges of those. And then you see here this pixel RDE and the edges of that. And so now if you compare, for instance, these edges with these edges, you see that there are additional edges, for instance, in this area, which appear. Whereas here, the edges are always a subset of the edges in the true image. And so also this seemed to be something which is a nice feature to not have the explainability algorithm inventing something in addition which wasn't present in the image. So then let's also look at other types of data. One is audio data, very classical. You have instruments playing, and then you can wonder for, you have, for instance, a neural network which classifies instruments, and you are wondering whether for this decision, magnitude or phase is more important. And so typically you would expect that an algorithm looks more at phase than at magnitude information. And so via this explainability approach, you can actually also show in that way that indeed the neural network looks more at phase information than at magnitude information. And last but not least, this comes from a very different application. So this comes from telecommunication. So what you see here is a city map. Yeah, so these blue parts are buildings. The red dots are cell phone users. The white part here is a radio tower, a telecommunication tower. Yeah, so, and now via this, what we call it, radio unit, that's an algorithm which now computes this black and white background, which is the radio map. And this black and white background tells you for each pixel how strong the signal there is. Yeah, so you see, if you stand here, the signal is actually really bad. Well, because there are also a lot of buildings blocking your signal from the cell tower. Yeah, but if you stand here, for instance, you're standing right in front of the cell tower. But now you can wonder why the neural network outputted the black region here, which is really strange. Because if you stand here, you stand right in front of the cell tower. So the question is, did the network do something wrong? Did it invent maybe something? And using this type of approach, you can ask the network, and showed you that this pixel, the reception of these cell phone users was important for the decision and these buildings. And these cell phone users have bad reception. And so what turned out in the end was that there was a building missing in the city map. Yeah, so that way you can also check whether neural networks did something wrong, and maybe they didn't do something wrong, but something was like here. I mean, there was something missing in the city. Okay, so let me conclude. So I think, to my mind, I mean, it's an exciting area, explainability. It's also extremely relevant because, I mean, in the end, the users will always have algorithms which were trained by other people, and so they need to be able to understand how decisions are reached. And so explainability aims for determining which input features are most relevant for a certain decision. So what I showed you here is one approach, and I think Klaus will show you a different path towards this problem. So here, this approach is based on information theory, rate distortion theory. We saw that it's a quite flexible approach. We can also, in particular, apply it to different type of representation systems, like, for instance, wavelets. And in that sense, one can also show that not only you outperform sometimes current methods, but you get also some additional insight, for instance, for adversarial examples. As I showed you, one can, in a certain sense, see what the network saw and then reached a wrong conclusion. And with this, I'd like to conclude, and thank you very much for your attention.
Thank you very much, Gitta, for a very exciting talk. Other questions in the audience?
Thanks for the talk, Kwaku Abraham, University of Cambridge. So everything you've talked about there is kind of post hoc, explaining the black box machine learning algorithm that you're given. So is there much research on building algorithms that from the start have explainability baked into them, and does that kind of lead in different directions, or is the kind of post hoc adequate to cover everything?
No, you're absolutely right. I mean, thanks for asking this question. I mean, there are already some approaches which build, let's say, in the neural network to some extent, or some maybe part of the network which aims for explaining later on the output. So there's research going in that direction, which I find also very, very interesting, and it's certainly relevant. I mean, still typically, I mean, if it's built in, it's usually also another part, like a neural network. And again, I mean, from my perspective, what I'm still a bit missing in the overall field is really a substantial theoretical foundation. But I mean, to answer your question, yes, there are results in that direction.
Thank you.
Thank you very much. More questions? No, there are questions in the chat, so maybe I can read them out. Okay.
Yeah, so shall I read it, or I mean, do you?
You're welcome to read them if you'd like to.
Yeah, I think the first question relates to, it was asked by Alex, whether, so here the explanations are always based for one particular input image. Yeah, so we always have the explanation targeted why a certain decision was reached for a certain input. And so the question Alex asked is whether one can have a universal importance map for a given network. I mean, certainly, let's say you have a class of pictures which are all, let's say, boats. You can take explainability or relevance maps for all those. You could try to average it, but I mean, it's the question: what is a universal importance map? Because in the end, I mean, what you would like to do is you would like to explain one particular decision. But sure, I agree with you. I mean, a universal importance map would be very nice. I just don't know at this point, I mean, how that could look like. So I hope that answers the question.
Okay, then the next question, maybe I'll read it out. From Lan H. What would be the approach for explainability when it is not supervised learning classification or direct labels, such as in explaining the policy of a reinforcement learning agent?
Oh, yeah, I cannot say, I mean, I'm not aware of any work in that direction. I mean, but that doesn't mean that there's nothing there, because it's such a huge field. So, I mean, yeah, I mean, sorry, I'm actually not aware of any results in that direction. But so here, yeah, so that's all I can say at this point.
Okay, thank you. The next question is by Amartya Banerjee. In the previous slide, well, whenever that was, were the images called adversarial examples in the sense that imperceptible changes were made to it, or is it because the images were naturally occurring outliers? If it is the first case, what sort of adversarial perturbations were the experiments focusing on?
Oh, I see. Yeah, so that's a good question. I mean, so the question is always what you define to be adversarial examples. I mean, often an adversarial example is deemed that, I mean, the human cannot see any difference. There is, let's say, a small perturbation. So here, what I just meant, I mean, is these are images which are wrongly classified. I mean, it's not that they are, yeah, so usually, I mean, you have an image and which is classified as something, you make a tiny perturbation which the human eye cannot see, and then it's wrongly classified. I mean, this is not of that type here. So here, these are just natural images which are wrongly classified because, in a certain sense, as we saw, the neural network saw something wrong in it.
Okay, thank you. Now, the next question is from Noshin. If there are such mistakes within the results of a model, is there a figure of fairness to measure the performance regarding wrong conclusions made by models? I mean, something that considers demographical attributes or so when it comes to sensitive topics like medical imaging or facial recognition?
Try to understand the question. I mean, yeah, so I mean, going to fairness, I mean, I think it's a big step from, let's say, these explanations. So the explanations for now just look at what the network presumably saw and put its decision on. Whether it's a fair decision or not, I mean, I think it's a different matter, because then you need to look at the overall context of the training data and so on. So in that sense, I mean, explainability is not really at the moment, I think, prepared for discussing questions of fairness, but I mean, it could be one part in the end, because in a certain sense, fairness and bias, so, or unbiased, I mean, there you usually have the problem that you have wrong conclusions. And so in that sense, you can then see whether network based it's on. Maybe you see that it based its decision on because it assumed that it came from a different, let's say, a different larger class. So for instance, I mean, you train your neural network, let's just on men, and you have just very few women, and maybe then you could see in the explanation that this is the reason why it was wrongly classified. But I think that's an interesting question, but I haven't seen any, let's say, explainability methods going in that direction.
Okay, thank you. The next questions is by Zahra Abdallah. It goes as follows: explainability in images is somewhere established more than other data types. Any example of similar approaches for other data types, for example, time series? And what do you think of a corresponding explainability notion in time series, similar to pixels in images?
Yeah, for instance, I mean, what you could do for time series, I mean, you have also different data representations, like wavelets, or if you have audio data like music, you have time frequency representation. So certainly, I mean, you could apply what I just show you, this algorithm, then to get relevance scores for the coefficients of that. So that should be possible.
Okay, thank you. Now the next question is by, Thomas Fink. Cartoon X is based on wavelets in order to explain decisions of a neural network. Do you expect that more information is obtained when using shearlets for that purpose?
Yeah, that's an interesting question. So we are also working in that direction. Yeah, so there are some advantages, but right now, I mean, we didn't see, let's say, such a tremendous advantage of using shearlets. I mean, there are some advantages which we detected. But one question is also, what is a better explanation? So here, for instance, the images, these wrongly classified images, which I showed you there, I mean, for wavelets, you already saw it quite nicely. For some shearlets, it's sometimes a bit sharper, but then the question is, I mean, what do you prefer? But yeah, I mean, it's something which we also analyze at the moment.
Thank you. The next question is by Robert Hassan. What is the approach when the input data does not have a natural representation? For example, when the input is survey data on a Likert scale, and the task is to hire or not. I'm not sure what the Likert scale is.
Yeah, me neither. But I mean, let me just give maybe a general answer to that. I mean, so these explainability methods always aim for putting relevance scores on features of the data, whatever feature is. So, I mean, you need to have some idea, I mean, what you would like to understand whether something is relevant or not. I mean, it could be, for instance, if you have, let's say, a hiring process, then the features could be, I don't know, I mean, certain parts in the application, like the age of the person and so on. Yeah, so I mean, you need to identify features, otherwise the algorithm cannot handle that. So in that sense, you need to have, yeah, that you need. I mean, because yeah, so there are some approaches where you maybe also can try to learn such a representation, but typically, I mean, you need to know beforehand which features are interesting, in general interesting.
Okay, thank you very much. Okay, many thank yous. Okay, I think that's it. Are there any questions in the audience? Yes, there is one.
Okay, thank you. So Carlos Esteve from University of Cambridge. So we have that the relevant part in an input, like an image, depends on the input. So we can define a map which, given an input, gives you the relevant part of it. Is there any result concerning the regularity of, or the stability of this map? And is there any way to ensure this stability during the training of the network? Because I think it should be desirable to have this kind of stability.
Sorry, say it again. Which map? So the map, which maps?
The map which
outputs
maps
to
the input to the relevant part of the input. So the relevant part of the input depends on the input.
Yeah, I mean, I think the problem is that networks are typically not robust. So in that sense, I mean, if you, for instance, have a so if you, for instance, modify your image just slightly, I mean, the decision can change rapidly, and then what you would expect is that also the explanation might change. I mean, might have a discontinuity there. So in that sense, I mean, I don't think you can expect that that map is smooth.
Okay, thank you. Are there any other questions in the audience? No? In the chat? No? Maybe I'll ask just one final question. In some sense, what neural networks do is learning features from data. So they sort of learn a different representation. And then what we do, or what you do in the explainability, in your explainability approach, is you try to understand whether features that are understandable to humans correlate with the features that the neural network learned in some sense. Isn't it a contradiction? That we want the network to learn something new that we didn't know, and then we see how different it is from what we already know.
Well, I mean, what you would like is, I mean, yeah, I don't see a contradiction with that, because I mean, what you would like is you would like to analyze what the network based its decision on. It could be that it's different from what a human would use. So for instance, I mean, that way you can also detect if something went wrong. So there's this example, which I didn't show you at this point, but I mean, let's say you have a data set where you have a certain, let's say, copyright mark on each of these images which you train on. Then the neural network would base its decision on this copyright tag, because it's much easier to look at that than look at the image. And so the explanation would then give that. And that would be an explanation, and that would be, let's say, a feature which would be different from what a human would look like, but this is maybe also something which you don't want. So in that sense, I mean, yes, sure, the neural network might learn some different features, but it's good to also control which feature it learned and where it based its decision on, to then also be able to understand it.
Thank you very much. Well, a question from Alex appeared. I think in a certain sense, it is a projection of the net back or onto an explainable basis, like pixels or wavelets given an input. Is that correct?
I mean, projection, yeah, I wouldn't quite phrase it that way. I mean, so these backpropagation algorithms, which I'm sure you will learn about tomorrow, these are more like a projection back. So they project basically back through the network on the input image. So here, yeah, I wouldn't view it as a projection that way.
Okay, thank you very much. I don't see any other questions in the audience or in the chat. So let's thank Gitta again for this exciting lecture. And we will reconvene here in 20 minutes for another lecture on robustness.